The next lecture is RF filters. Now we start with introduction. A circuit that allows the specific range of frequencies to pass through it and blocks all other frequencies is known as a filter. The four major types of filters are low pass filters, high pass filters, band pass filters, notch filters, or band reject filters. All of these filters are shown in the figure. A low pass filter passes low frequency components of an input signal, while a high pass filter passes high frequency components. A band pass filter passes a narrow range of frequencies centered around the filter's resonant frequency, while a notch filter, that is, a band reject filter, passes all frequencies except those within a narrow band centered around the filter's resonant frequency. There are a number of practical applications of the filters in electronics. The unwanted high frequency noise present within the AC line voltage in a DC power supply can be eliminated by using filters, and the pulsing DC voltages can be flattened out that are generated by the rectifier section of the supply. In radio communications, the listener at the radio receiver is provided with only the desired signal while all others can be rejected. Only one signal is allowed to be generated at a radio transmitter by filters, while the other signals that might interfere with different signals of the different radio transmitters are attenuated. In audio electronics, the low audio signals are diverted into woofers, middle range frequencies to mid range speakers, and high frequencies to tweeters by using filter networks, which are also known as crossover networks. Next is passive filters. The passive elements, example resistors, capacitors, and inductors, are used to design the passive filters and are responsive to frequencies between around 100 Hz and 300 MHz. There is an increase in the number of sections of inductor and capacitor when passive filters are designed with very steep attenuation fall-off responses. More the sections added for getting the desired result, greater the chances of loss of a signal. There is a need for taking into consideration the source and load impedances when designing passive filters. Next is active filters. Operational amplifiers, resistors, and capacitors are used to construct the active filters without any need for inductors. Very low frequency signals are handled by the active filters and voltage gain can be provided if needed. The designing of the filters can be such that their performance should be comparable to LC filters. The construction of active filters is easy, less finicky, and there is no need for large-sized components for their designing. As desired input and output impedance, independent of frequency, can be provided with active filters. The active filters provide relatively limited high-frequency range, which is their major drawback. Active filters become unreliable above 100 kHz. So passive filters provide reliable performance at radio frequencies. Next is key parameters to describe filter response. Minus 3 dB frequency, that is denoted by F3 dB. This represents the input frequency that causes the output signal to drop to minus 3 dB relative to the input signal. The minus 3 dB frequency is equivalent to the cutoff frequency, the point where the input to output power is reduced by 1/2, or the point where the input to output voltage is reduced to 1/f. For low pass and high pass filters, there is only one minus 3 dB frequency. However, for band pass and notch filters, there are two minus 3 dB frequencies, typically referred to as F1 and F2. Center frequency, that is F0. On a linear log graph, bandpass filters are geometrically symmetrical around the filter's resonant frequency or center frequency, provided the response is plotted on linear log graph paper. For narrow band bandpass filters, where the ratio of F2 to F1 is less than 1.1, the response shape approaches arithmetic symmetry. Passband. This represents those frequency signals that reach the output with no more than minus 3 dB worth of attenuation. Stop band frequency, denoted as Fs. This is a specific frequency where the attenuation reaches a specified value set by the designer. For low pass and high pass filters, the frequencies beyond the stop band frequency are referred to as the stop band. For bandpass and notch filters, there are two stop band frequencies, and the frequencies between the stop bands are also collectively called the stop band. And last is quality factor, denoted as Q. This represents the ratio of the center frequency of bandpass filter to the -3 dB bandwidth. So this is all in this lecture. Thanks.